Good morning, good afternoon, and good evening, everyone. I am Praveen from marketing team of Tata Elxsi. It is great to see how many of you have joined us, and I welcome all of you to today's webinar on intelligent battery systems, hosted by Tata Elxsi. Batteries are a vital component of every stakeholder's electrification strategy, whether the manufacturer is concerned with driving performance, safety, cost, or the end user experience. Batteries are at the center of discussion. Today, we have with us Mr. Perumal, Head Mechanical Design, Mr. Anush, Technology Manager for EV, and Mr. Nijesh, Senior System Architect, Vehicle Electrification, to give us insights on a design-led approach for accelerating e-mobility through intelligent battery systems. We encourage you to ask plenty of questions. At any point during the webinar, please type your questions into the chat box that you can find on the screen. At the end of the presentation, your questions will be taken up by the speakers and will answer as many as possible. Perumal, Anush, and Nijesh, it is a pleasure to have you all with us today. And I welcome Perumal now to take the control and begin the session. Thank you.
Thanks, Praveen. Once again, I welcome all of you and thanks for joining this session today. Before getting into the main topic, I would like to give you a quick overview about Tata Elxsi. Tata Elxsi is an integrated design, engineering, and technology company based at Bangalore. And we do consumer research, technology consulting, product design, development, testing for various industries like transportation, media and communication, medical electronics, etc. All these things being enabled through a core team of 8,000 engineers and technologists who work from different locations in India and supporting our customer across the globe. So in automotive, we work for last 25 years. With this experience, we are bringing together a world-class embedded mechanical testing, artificial intelligence and IoT practices and award-winning HMI team backed by ASPICE process. With all these enablers, Tata Elxsi is driving solutions for connected, autonomous, shared and electric vehicles of the future. With this short introduction, I will move on to the content for this today's session. So we have 5 different segments today. We start with introduction to intelligent battery system, followed by a segment each for the important enablers we makes this battery more intelligent, and we can also see some of the challenges associated with these enablers and some of the solutions. So one of the solution is or one of the enabler is mechanical design, how that mechanical design will contribute to intelligent battery, that will be covered by myself, and followed by a segment on intelligent battery management system will be covered by our technology manager, Mr. Anush Noyer, and another segment on battery digital twin and cloud BMS will be covered by Mr. Nijesh PS is our senior system architect. In the conclusion segment, we can see all the challenges what we discussed in this session and some of the Tata Elxsi solutions to address these challenges and in this intelligent battery system space. Talking about intelligent battery systems, the battery pack is one of the sizable system in electric vehicle, as its volume, the weight, cost, and the range dependency makes it more significant in the electric vehicle. Right, so there are a lot of innovations and there are a lot of innovation and optimization happening in battery system. So to make this battery more intelligent in terms of design, control, and predictability and connectivity to serve better serve the better performance and safety and meet to the safety expectations. So in this session, intelligent battery system, so it gives you some insights about how some of the smart designs like having a modular battery architecture, using the lightweight material for the structures, and adopting unconventional cooling methodologies alongside effectively controlling and maintaining this battery pack through intelligent battery management system we can see here. And as you all know, BMS design is having a lot of challenges, ranging from cost and design optimization, maintaining the software complexity, and it is also having problems from the security threats, right? Security, all these challenges are there apart from its regular performance requirement. So we can see in this session how we can address all these challenges in BMS through modular, scalable, and distributed hardware, and also how we can do it through advanced algorithms, and how we can do this through connected and cloud BMS on digital twin or AI platforms. This session also covers a bit about battery digital twin and digital twin framework and its relevance with cloud BMS. And we are also having some snapshot on some of the microservices which enables this battery pack to work more intelligent and smart. So these are the things we are covering in today's topic. I will move on to mechanical design enabler, right? So here we can see how a lighter, safer, and purpose-built battery packs can be achieved through better mechanical design. Okay, we always have a debate, or we can say we can always have a challenge on deciding upon the size of the battery pack. So whether we want to have a small or compact battery pack, or we want to have a larger battery pack to have more range, to get the more range. So there is a smart play required here to have the optimum battery pack by managing all these influence factors. The first and foremost is the range. The range is always the significant factor in the EV, and it is more attractive as well because in the mobility application, because it is a sellable matters for the mobility application. So how we will get more range in the vehicles, right? So the energy available in the vehicle for tractions decides the range of the vehicles, right? So if we could able to store more energy in the vehicle, then we it appropriately that or proportionately that range also will be high. So if we want to accommodate more energy, obviously we may need a larger volume in the vehicles. If there is a larger volume, then your battery pack size will go bigger and bigger. If the size increases, the another one obviously increases is weight. Weight also will be increases, and it may lead to a lot of dynamic changes in the vehicle performance, right? So if you look at the cost of the battery pack in the modern day battery packs, nearly 25 to 20%, 25 to 30% of the vehicle cost incurs only for battery alone. The another important factors to be considered is safety, because all these battery packs are operating on high voltages. It possesses the vehicle and passengers safety when there is a vehicle crash event happens. So all these factors influencing on battery pack geometry, deciding on the battery pack geometry size, and the mechanical design can be more smarter if we get more energy density in a small package volume, right? So to have that, we have to smartly choose and package the energy dense batteries first, right? So currently the cylindrical cells are widely used, but prismatic cells are uh, also getting attention nowadays because it have options of having ease of assembly and better serviceability options. And also, if you look at the complexity wise, it is so comfortable with respect to having less number of cells in a complete battery pack. There are other two aspects to be make this battery pack much more smarter, or adding structural strength to this battery pack by choosing very appropriate purpose serving materials, and also having a very efficient thermal management system in the battery pack. I leave a thought here to have two battery pack in a vehicle. It means if a vehicle having two battery pack, one will be permanently fixed in the vehicle and another one will be a swappable option. We understand that it will disturb the energy management in the electric vehicle, but it really relieve the customer from their range anxiety. Another factor to be considered is the battery pack architecture, how this will help to have a smart and intelligent battery pack. We'll see here. We'll start with the light weighting. Nearly 55% of the weight of the battery pack have been contributed only by cells, right? So if we want to do any opportunity, we have opportunity to optimize only from the remaining parts, which contributes 45% of the weight. So if you look at what is there apart from cells in the battery pack, we have module structures we are having. We have all the enclosures, frames, lids, additional things we are having, and we are also having the thermal management systems, right? Is there any way to reduce these weights here? There is a concept gaining attention nowadays, cell to pack architecture. It's completely eliminate the module structures, and it will give you considerable volume to have more number of cells inside the battery pack. So prismatic cells are widely used in this cell to pack architecture, even though cylindrical cells are having more package density and physical density. Why say prismatic? Because of its convenience to use, as well as the form factor is very much playing role here. And another aspect to look at is your battery structure should be robust, right? So we should have the battery pack architecture, whatever we are choosing, should have opportunity, or it should have a mechanism to isolate the vibration to cells and all the internal electrical connections as well as components. So these frames and enclosures are the important structure. Battery will become a structural element in vehicle. So the material used for designing any of these structural components to be precisely be chosen. So generally high strength metal alloys are being used. So we can replace them by using carbon fiber or epoxy based composites, or we can also use hybrid and reinforced structures, okay, reinforced materials for these structures. And for to maintain the modularity and scalability, it is very much possible, or it can be achievable if you have very smart battery pack, battery packaging, battery cell packaging, and modular packaging, and if you choose the appropriate thermal management strategy. Another factor here, it's very much contributing for smart battery pack design is how we do mechanical interface design, and how one choose the material for these structures, right? Battery pack is having multiple components, right? Multiple component inside. It has cells, it has electromechanical component like bus bars, it's having a thermal interface material, frame structures and joints and so on. So many components it's having. So choosing an appropriate material for all these components contributing the weight and cost of this vehicle, right? So if you, for the instance, if you look at the electromechanical components like bus bar, generally we will use copper for bus bars. And because of its thermal conductivity property, right? It is very superior in thermal conductivity. But on the other hand, if you look at that, weight of that copper is very high. So if you go for an approach of having aluminum along with copper, if it and assessing them for its the performance, and if there is any problem, if you mitigate the problem and use those aluminum along with copper, it will heavily benefit to reduce the cost and weight. And another important element of this battery pack is the frame and enclosures. And these enclosures are the outer surface of the battery pack. It physically protect all the internal components inside the battery pack. So for the such application, normally we'll go for high stiffness and high strain energy materials. Normally it will be used. Currently extruded aluminums are widely used in this case. So as I indicated earlier, we can go for composites. It's obviously will give you the same performance or of the material used currently. Also, it significantly reduce the weight. And another important aspect is mechanical fixings, right? So fixings for modules or the entire module, entire pack to vehicle fixing, it has to be designed properly so that we can establish the a proper load transfer path, and it is very much useful to, it will very much useful, and it will transfer the load, external loads, and also protect or also keep the battery pack intact when there is a event of vehicle crash happens. So mechanical fixing design also equally important in smarter battery pack design. So another aspect, important and crucial system in battery is thermal management, right? So if you want to have a modular and scalable design of a battery, then your thermal management system also should be modular. This will improve the battery life as well as it prevent the extreme thermal events like thermal runaway. Generally, we'll use two different cooling system. One is air direct cooling, and another one is cold plate indirect cooling. Generally will be employed in battery management system. So passive or active air cooling is employed when there is a need of having a reduced heat rejection, but it obviously too it take 2 to 3 times more energy than the any other cooling any other system which used uh, liquid cooling, right? So liquid cooling. So the another cooling plate, another liquid, another cooling system we use is cold plate indirect cooling, and this is what widely used nowadays in battery packs. Even though it is having its own challenges like limited thermal conduction, right? So because in a liquid cold plate cooling, so we have more than one material between the cells and the coolant. So it is the conductivity will be limited here, and this also will take considerable energy and to take away the heat from the entire battery pack. So choosing the appropriate material and effective packaging, it helps us to have better performance in even in cold plate cooling. Another technology or methodology, the thermal system methodology is gaining attention nowadays is immersion direct cooling. That system use dielectric cooling for that cooling purpose. It will have a direct contact with the cells, so it will effectively take away heat because we that cells are directly contacting the dielectric liquid, and also there is no material between cell and coolant, and it offers a very good thermal runaway protection. But this system also have some challenges because it is all these cells are being flooded inside the coolant. It demands a very effective sealing, and also the flow arrangement between module to module has to be established properly. So these are the some of the challenges, and also it significantly increase the weight of the entire pack. These are some of the challenges from immersion direct cooling. So we have some graph here, so we can see some of the comparison between immersion direct cooling and cold plate cooling. If you look at the top two graphs, it shows that in the lower discharge rate, if you look at both cold plate cooling and immersion cooling are having performance very similar. But when that C rate increases, immersion cooling outperforms in the cell level. But surprisingly, if I look at the module level, that temperature difference is very high in immersion cooling. And if you look at the bottom two graphs, it shows that that cooling rate is very low in the immersion cooling at the low coolant flow rate, and considerably going further low when we are increasing the coolant flow rate. And the same way in the module, if you look at a low coolant flow rate, immersion cooling, and the temperature difference is slightly high in immersion cooling, but it is considerably getting lower when we are increasing the flow rate of the coolant. This is about that comparison. So obviously the thermal management is completely controlled by BMS. BMS is playing a vital role in controlling the thermal behavior of the battery pack. BMS is the brain of the battery pack, we can say. So to talk more about BMS and how we can do a smart and intelligent BMS, to get the robust and consistent performance of battery pack. That will be covered by Mr. Anush. I request Anush to take this session from here. Thank you all for your patient listening. Thank you once again. Anush.
Thank you. Thank you, Parimal. Hello, everyone, and welcome to the next segment. In this segment, we will look at more at the battery management system, its role and functions in the battery system and the whole electric vehicle. Let us look at some of the driving factors behind the evolution of BMS in the electric vehicle. The main thing is that the lithium-ion batteries, which are some kind of default choice when it comes to selecting a battery for EV application, they have some risk element associated with that. They are somewhat unstable in nature. As Parimal mentioned, there is a chance of thermal runaway and explosion associated with these lithium-ion batteries. So there needs to be an electronic system which constantly monitors and make sure that the battery is performing in its safest zone. So thermal management and making the battery pack safe is a critical function that is performed by BMS. Next thing is that the batteries, the lithium-ion batteries are having non-linear charging and discharging characteristics. So that makes it difficult to do estimations of the internal states of the battery. For example, the state of charge and state of health, which are indicators of the range that is achievable from the electric vehicle. So it is extremely important to have accurate estimations of these parameters to provide the correct and accurate values of these parameters to the vehicle as well as to the driver for optimal vehicle performance as well as user experience. We have to consider the aging effects of the battery as well here for getting the accurate measurements and estimations. Then another factor is that the lithium-ion battery packs are made up of a number of cells which are combined into a number of modules, and then those modules combined into make the entire battery pack. And there can be imbalance in the charge level and voltage level in the individual cells and the modules. That effectively reduces the capacity utilization of the battery in the long run. So a system has to be there to make sure that the charge level in the individual cells are balanced properly so that the utilization is better and also the battery is operated in a safer manner. So that is a part of the overall optimization. When you talk about optimization, we had to think about extending the life of the battery as well, because battery is the costliest element in the vehicle, as Parimal also suggested. So it is extremely important for extremely important to make sure that the user gets the maximum out of the battery's life in order to have a sustainable EV ecosystem. We can also see that an accurate and robust battery management system also provides tighter design margins. It is enabling tighter design margins and giving freedom to the vehicle designer and thus achieve better optimized vehicle designs. So that will result in optimal battery pack, which is having a lesser size and weight and better range, and also will result in cost optimization. It will also result in cost optimization through optimizing the number of sensors, computing platforms, etc. So overall, we can see that the battery management system is a critical element in the electric vehicle as well as the electric vehicle ecosystem, and it performs three key functions, that is monitor, protect, and optimize. In the next slide, we will see some elements of the battery management design. So when you talk about the design considerations, we can see that there can be a number of design considerations, starting from battery configuration, the requirements from the sensing side, from the functional side, from the performance side. The battery management system design can change with respect to the vehicle architecture, the interfaces, the connectivity requirements can change for different type of vehicles. There can be swapping requirements, then safety, availability, and cost. All these factors are deciding factors in the battery management system design. As an example, we look at three categories of vehicle as shown in this diagram. You can see a scooter, you can see a four-wheeler, a passenger car, and a commercial vehicle, an electric bus. If you look at the battery management system for a scooter, I have shown a simplified diagram of the battery management for a scooter. A scooter typically will have a single battery module. For example, a 2 kilowatt hour battery module, which is having say 15 cells in series, which will produce a 48 volt battery system. So you may basically require an analog front-end chip which can monitor these 15 cells and get the measurements such as voltage, current, temperature, etc. And the processing of these sensor measurements and the control functions, the monitoring functions, etc., can be done by a microcontroller. All these elements, the battery cells, the microcontroller, the AFE chip, etc., as well as the discharging circuit, all these things can be enclosed inside the battery module itself. So when you talk about a two-wheeler, there can be requirements like a removable battery, where the battery can be swapped or the battery can be taken to home for charging, etc. So that makes it important to have connectivity with the user mobile application as well as facility for tracking. So those interfaces are also required. For example, a Bluetooth connectivity can provide connectivity with the user mobile application, and a 4G LTE connectivity connection can provide the connectivity with a cloud system which enables tracking. When it comes to a four-wheeler, a passenger car, for example, there you have higher voltage batteries with a higher kilowatt hour capacity, and they typically are not swappable because of practical difficulties. So the BMS design also will change with respect to that. Here you can see the number of modules are more, and you may require a battery monitoring system within the battery module itself, and the BMS can have a master-slave architecture in this case. So the BMS can be divided into two parts. One part, that is a master, which will sit outside the battery pack and receive the information from the battery management system slave units, which will take the information from the individual cells and modules and pass it on to the BMS master. When it comes to a commercial vehicle, which will have a bigger battery pack, the architecture will again change. It will have a number of strings which will all be connected in parallel, and there will be an additional multi-string control which will look after the functions such as string management, in addition to the BMS master and BMS slave units which are there inside the individual strings. So you can see that the complexity of the BMS design changes with respect to the vehicle segment. With the advent of distributed computing, high-performance computer platforms, etc., in the automotive domain, and the BMS design also has undergone changes. So here the BMS designer gets some more freedom to have more complex functions which can be run on the domain controller, domain controllers, which are higher performing, which have high performance capability. So there, the BMS master can be a less complicated system, and it can be more optimized, and the functions such as the state of charge estimation or state of health estimation or prognostic functions, things like that, can be hosted on the domain controller, and they can be availed as and when required by the BMS master. So there is a shift towards software complexity, which can be managed through service-oriented software architecture, etc. The increased software complexity is a penalty in this case, though. An extension of this approach is a cloud-enabled BMS, where more complex functions can be hosted on the cloud and interface through the telematics control unit of the vehicle itself. So in the next segment, Nijesh will be talking more about the cloud BMS and its features. Overall, we can see that the design challenges associated with the BMS is something like, one of them is achieving a generic design with respect to various requirements, various vehicle segments, etc. Ever-increasing performance and functional requirements will increase the software complexity. Hardware design challenges will be there with respect to change in voltage levels, 400 volts to 800 volts to beyond 800 volts. When the battery pack voltage increases, the BMS also has to accommodate that. When it comes to cloud BMS, managing the connectivity issues and cybersecurity will be problems or challenges to take care. Now, in this slide, we will look at how an intelligent BMS can provide value across the life cycle of the battery. That means from the manufacturing of the battery through the use of the battery in eMobility applications, the use of the battery in a second life application such as energy harvesting, and the recycling of the battery. So one feature that is provided by the BMS can be traceability through life, which can be achieved through something known as a battery health passport. This is nothing but a storage mechanism coupled with a RF identification, which will store the battery configuration as well as key usage data. So this will enable better decisions when it comes to repurposing the battery for second life, when it comes to recycling the battery, etc. So this can even enable. You can see that it will enable a circular kind of economy where the recycling of the battery that will give the precious raw materials for the fabrication of newer batteries. Intelligent software features, we have seen some of the features like monitoring, protection, estimation, etc. So they will all help in better management of the battery's life as well as performance. One aspect that is followed, one methodology that is followed in development of the battery management software is the mathematical modeling approach. So that will enable to have a better understanding of the internals of the battery, the functioning of the battery, the aging characteristics of the battery in a better manner, and that will enable better prediction of the battery states, better prognostics, and it will result in overall better management and extension of life of the battery. Telemetry enabled BMS will provide value in the way of analyzing the data that is obtained from the BMS through cloud connectivity, then fault detection, preventive maintenance, etc. Live software updates is another factor. It will also help in scheduling the hardware changes. We'll now look at some of the leading trends in EV batteries and battery management systems. Sophistication in BMS software is increasing, and more and more complex battery models and battery management system models are evolving. Multi-physics based battery management models that self-optimize, and those models which are AI enabled, which can self-update and parameterize. These are some of the leading trends in the software area of BMS. I mentioned about the high voltage, the trend towards higher voltage architectures. So present day vehicles, most of them are working on 400 volts, but there is a trend towards 800 volts, which will help in faster charging and reduction in the harness size. Even 1200 volt systems are used in off-highway vehicles, and BMS needs to be scalable and adaptable for these kind of voltage levels and different architectures. Advancement in battery monitoring is happening in a gradual way. There are efforts in reducing the number of sensors by the way of sensor modeling. There is also this trend towards smart embedded sensing, which will enable one to monitor and control individual cells, enable one to isolate a particular cell in case of a cell damage, to extract power from only a certain number of cells, etc. are possible by this approach. Self-healing and extending the life of these cells, that is another trend that is happening in the research field. Cloud-enabled BMS is a mega trend which is happening at the moment. Digital twin is a key element, a hot topic in the cloud-enabled BMS area. So I would like to wind up here and pass over to my colleague Nijesh, who will be talking about the cloud-enabled BMS features and especially the battery digital twin. Thanks very much. Over to you, Nijesh.
Thanks, Anush. Hello, everyone. In this part of the session, we will discuss more about digital twin concept from a battery perspective and how the battery digital twin helps improve safety and performance of a battery system and also enhance user experience. So before we start with the digital twin, let's have a quick look at the major challenges faced by a conventional onboard BMS and how a cloud-based BMS approach can address those challenges. As we know, the requirements of the battery management system are ever growing for optimizing the performance, ensuring the safety of operation, and extending the cycle life of batteries. So the next generation BMS needs to have advanced functions like highly accurate state estimation, proactive thermal management, smart charging control, prognostics, and intelligent energy optimization. These functions also need real-time and detailed information about battery pack, preferably at module level or cell level. But the onboard BMS only receives limited information from a real battery. So so hence more information about the battery pack is required for the optimal control of the battery system, like detailed internal states and usage history. For example, calendar age, charging, discharging cycles, and ambient temperature range, etc. So to address this problem, the general trend is to use high fidelity plan models combined with some smart machine learning algorithms for predicting the battery behavior and detailed internal states. However, these models are too complex to run on an onboard BMS due to its limited computing power and data handling capabilities. So the solution is to deploy such complex models and algorithms on a scalable, secure, and reliable cloud platform that provides high computing power, enormous data storage, and support for big data analytics. In such a case, the BMS will be distributed across vehicle and cloud platforms with a real-time connectivity for continuous data exchange between the two platforms like physical and virtual platforms. In such a distributed architecture, the onboard BMS will host all the basic functions while the complex algorithms are deployed on the cloud part. So this approach makes the solution scalable for different applications because the features on the cloud BMS can be customized for various target applications. So to summarize, the plan models running on the cloud platform together with the smart algorithms can be considered as the digital twin of the physical battery. So let's check what exactly is a digital twin or a DT. A DT is a digital replica of a physical entity running on an off-board platform with a close data connection between the two. In fact, the DT itself is not a new concept. The idea of DT was first proposed in 2002, and later NASA introduced the concept in 2010 in their space missions to ensure the safe operation of the flight system. From there on, the digital twin concept has been used in aerospace application quite a lot, mainly for prognostics and planning maintenance of the systems. Now, adoption of this concept to automotive domain is gaining traction recently, especially in autonomous driving and EV applications. So as we know, battery pack is a major component of any electric vehicle, and it degrades over time due to aging, and this adversely affects the performance of the overall system. Moreover, the rate of degradation of each battery may be different depending on the specific usage patterns and environmental conditions where it was deployed. So it's very important to track each battery individually. So the digital twin of a battery pack is a set of high fidelity plan models that address geometrical, electrochemical, electrothermal, and aging characteristics of the battery. These plan models are updated real time with the physical battery data so that it resembles the real battery in all aspects always. As I mentioned earlier, the number of parameters published by an onboard BMS are limited. But using this limited data, digital twin will be able to estimate and visualize the detailed internal states of the battery, even at cell level, with the help of the plan models. So the primary use case of a battery digital twin are for simulation and analysis of complex scenarios that helps optimize the design. Real-time monitoring and prognostics like thermal runaway prediction, remaining useful life prediction, predictive maintenance, etc. Another use case is proactive control of battery system for ensuring safety of operation, improving performance, and optimizing the energy consumption. So as we discussed already, the key challenges associated with the digital twin are the accuracy of the plan models, high computing power requirements, real-time connectivity, network latency, and cybersecurity. So the technologies such as cloud computing, big data analytics, AI, IoT, and blockchain, etc., are employed to overcome these challenges. The digital twin concept can be used throughout the development and deployment lifecycle of batteries. The plan models and algorithms will continuously evolve from concept phase to maturing towards a deployment phase of the battery system. In the next slide, we will see how battery digital twins are deployed. Here the figure shows a high-level framework for DT deployment. The framework includes an onboard battery system and its off-board counterpart. The onboard system consists of battery pack, battery management system, and associated sensors. The off-board system is a cloud platform where the digital twin of the battery, cloud BMS functions, data visualization, and other value-added services are hosted. The onboard system will also have access to big data, including the data from other vehicles, map information, weather information, traffic information, and charging infrastructure information, etc. So once deployed, the DT will get refined based on the data from real battery, and the accuracy will be improved continuously over time. So cloud BMS will use information from digital twin and physical twin for monitoring the battery states and controlling the operation of the physical battery. At the cloud side, sophisticated algorithms are used for implementing complex BMS functions like thermal runaway prediction, remaining useful life estimation, etc., and also other services like smart range prediction and trip recommendation. Customizable GUIs can be used for data analysis and visualizing the parameters and internal states of the battery pack. Developing an accurate plan model is a major challenge here due to the unavailability of detailed battery characteristics data, either from rig test or from vehicle test. So different methodologies are adopted for the model development depending on the target application. The figure here shows the commonly used approaches for battery plan modeling. There are two types of models primarily, empirical and physics-based. The equivalent circuit model is an empirical one, which is simple and lightweight. And so it's suitable for real-time application. But the accuracy of the ECM is comparatively less, but it can be used for low-end applications. On the other hand, multidimensional multiphysics-based models are highly accurate, and they include electrochemical, electrothermal, and aging behaviors of the battery. But these models are complex and need detailed battery characteristics data for developing these models. So that's a real challenge. Also, the computation time of multiphysics model is high, and hence they would not be suitable for real-time applications. But these models are highly useful for simulations. Well-known tool vendors like ANSYS, Siemens, and COMSOL, etc., provide toolchain for multiphysics modeling. Another approach is to generate reduced order model or ROM from multiphysics models. ROMs generally have a moderate accuracy and moderate computation time compared to multiphysics models, and hence they can be used for deploying on cloud-based solutions. Another method that is getting popular these days is AI-based approaches in which a neural network model is trained with the data generated from multiphysics models or the data from real vehicles. So optimized ANN models can have lower computation time and higher accuracy. So ANN models are more suitable for advanced applications. But another challenge we have here is the validation of the plan models. The initial versions of the plan models can be validated with the lab test data or vehicle test data. But once deployed, the models can be validated with the real vehicle test, real vehicle data. The models need to be refined and updated at a regular interval in that case. Here we can see a snapshot of the functions and or services enabled by TT that Tatflexi is currently working on. We normally follow first principle modeling, including multiphysics or data-driven modeling approach for the development of DT and DT-enabled services. And in some cases, a hybrid approach would be more appropriate, depending on the complexity of the application and availability of data. Let's look at some of the interesting features that we are working on. For example, a safety feature, cell temperature estimation, that helps optimize the number of temperature sensors in a battery pack. This also helps determine the optimum mounting position of temperature sensors within the pack through by simulations. This feature also enables proactive thermal management and safety control. Another feature is the driver characterization that helps classify vehicle usage patterns based on energy consumption rate, and it tags the classification to individual driver IDs. This information will be helpful for making strategies for extending battery life with respect to usage patterns, and also for estimating the accurate range and optimizing the operational cost for fleets. Another interesting feature is a smart range prediction feature, which enhances user experience by estimating the range accuracy based on route information, map information, driver characteristics, terrain, weather, traffic conditions, etc., in addition to the normal battery and vehicle parameters. Trip recommendation is another feature that provides route recommendations for the journey based on battery SOC, SOH, availability of charging stations en route, and estimated time of arrival, etc. So to summarize, a purpose-built optimal battery pack with a modular, scalable, and intelligent BMS backed by a digital twin with smart algorithms ensure safety, longer battery life, and optimum performance. This approach also helps reduce the overall cost of ownership. Also, the value-added services offered by cloud-based digital twin enhance user experience. Let's have a look at the Tatflexi solutions to address the challenges we discussed so far. Tatflexi has developed a solution for a modular battery pack. The solution includes a simple and scalable frame structure, considering structural and thermal performance requirements. Tatflexi also has a design for a modular and scalable BMS with advanced connectivity features. The design consists of BMS master, slave hardware units, BMS application, and BSW modules. The BMS is configurable for battery packs of different types of vehicle. For example, mild hybrids, full EVs, electric buses, and trucks. We are also working on developing a framework for battery digital twin. The solution includes a number of value-added features enabled by TT that can be integrated to customer cloud platforms in addition to the advanced BMS functions. With that, we are concluding the presentation, and thank you for your attention.
We are always excited to join hands with you to support your journey in building the future mobility. Come, talk to Tata LC. Visit our website or drop a mail at info@tataelxc.com.